Hey, welcome back to your favorite pre-calc class. Take a look today at real zeros of polynomials. Last time we learned how to divide polynomials, so now we're going to apply the remainder theorem and the factor theorem. So the remainder theorem says if f of x is divided by x minus c, then the remainder is f of c, actually. Okay. So for example, let's take this first one, f of x here. Let's divide it by x minus 2. So let's take this 2x cubed minus 4x squared plus 5x minus 3. Let's divide it by x minus 2, but let's go ahead and do it with synthetic division. So I got the 2, negative 4, 5, and negative 3. And let's see what we get here. So I drop the 2 straight down and multiply it by the 2 times 2. I got 4, negative 4 plus 4, 0. 0 times the 2 up there is 0. 5 plus 0, 5. 5 times 2 is 10. So negative 3 plus 10 is 7. So this has a remainder of 7. So when we divided it, we ended up with 2x squared plus 0x plus 5. And then down here, we get this remainder of 7, right? Plus 7 over x minus 2. Well, this remainder theorem is saying if this is my original function, my dividend, if I'm dividing by x minus 2, whatever that term is, right, x minus, in this case, the 2, if I just plug it in, that's my remainder. It's actually my remainder. So if you can identify x minus c, if you can identify the c, you plug it in, it'll tell you if you have a remainder or not, right? If you end up with 0 when you plug it in, that means it divides into it cleanly, right? So the factor theorem, this second one right here, I just put an arrow on, the factor theorem says if my remainder is 0, then x minus c must be a factor. It must be a clean factor of that dividend. Okay, so that's the remainder and the factor theorem. So is x equaling 2 a 0? No, it's not, because when I plugged it in, I got 7. My remainder is not 0, so it's not a clean factor. So let's do some more here. Given this function, find f of negative 5. So we'll go ahead and throw in negative 5. And this actually ends up being 0. So that means our remainder is 0. That means it's a clean factor. In other words, if I'm taking this original 2x to the 4th plus 12x cubed plus 6x squared minus 5x plus 75, and I'm dividing it by x plus 5, right? I'm dividing it. It's kind of like if I had 8, and I know one of the factors of 8 is 2. If I divide 8 divided by 2, I get 4, right? It's a clean factor. So we're going to go ahead and do the division and show that it's a clean factor, right? So we're going to go to the side, 2x to the 4th plus blah, blah, blah. We're going to divide it by x plus 5, but we're going to use synthetic division. So this is the same as x minus negative 5. So negative 5 goes up there as our c term. Let's go ahead and put in the coefficients of our dividend. So 12x cubed, 6x squared, minus 5x, 75. And let's verify that it goes into it cleanly. So the 2 drops straight down. 2 times -5, -10. 12 minus 10 is 2. 2 times -5, -10. 6 minus 10, -4. -4 times -5 is 20. -5 plus 20, 15. 15 times -5 is -75. And sure enough, it has a remainder of 0. So this is what we get for our divisor. So 2x 1 degree less to the third plus 2x squared minus 4x plus 15. It's a clean factor, that x plus 5. So is x being -5 a 0? You bet it is. -5, x minus -5 is a factor, so -5 is a 0. It's there. It's the remainder 0. All right, solve the equation given that -2 is a 0 of. So notice they have f of x equals 2x cubed minus 3x squared minus 11x plus 6. So let's say and solve the equation if f of x, if y is 0, y is 0. In other words, what are my x-intercepts? Well, they're telling us -2 is a 0. -2 is a 0. They're already giving you one of them. So, number 1, if -2 is a 0, then x minus -2 is a factor. It's a clean factor. So let's go ahead and start factoring this. 2x cubed minus 3x squared minus 11x plus 6. Since we know that -2 is a 0, x minus -2 is a clean factor. But we've got to figure out the rest of this. So we're going to have to take that 2x cubed minus 11x squared minus 11x minus 6 and divide it by that x minus a -2. So -2 goes in the box. My divisor coefficients are 2x cubed minus 3x squared minus 11x plus 6. Now, they already told us that this is a 0, so I know it's a clean factor, so I better have a remainder of 0 when I do the division. So I'm going to drop that 2 straight down. I'm going to multiply it. 2 times -2 is -4, -3 minus 4, -2 times -7, 14, -11 plus 14, 3. 3 times -2 is 6, 6 minus 6, 0. Sure enough, it is a clean factor. So here's my coefficients of my divisor. So I'm going to put that in. 2x 1 degree less squared minus 7x plus 3. 2x squared minus 7x plus 3. And then I'm going to go ahead and keep factoring this. So I have this x plus 2. Now let's go ahead and factor this 2x squared minus 7x plus 3. So it's got to be 3 and 1. Looks like that'll be a -1 and a -3, and that'll give us, that's the correct factorization. Since it's a quadratic, right, I'm just going to go ahead and factor that quadratic. And we're solving this equal to 0. So x plus 2 equals 0. We already knew this one. We're going to take each of these factors equal to 0. So add 1, divide by 2. So we got a half, and we got 3. Right, those are our other ones. And of course, we had the original -2 that it gave us as well. So we just solved that equation by factoring it, given that they told us one of the zeros. Okay, if they give you a 0, then they're giving you one of the factors. You can start dividing. Unlike that last problem, sometimes we don't know what the zeros are. And so that's where this rational zeros comes into play. It says, I'm going to give you a list of possible rational, at least rational zeros, possible zeros that you can try. And it will be factors of the last constant term over factors of that initial leading coefficient. Okay? So this one, I can't factor. This is a third degree. It's not like I can factor it by grouping or anything. So I would like to know, what are my possible rational zeros? Well, it would be factors. So what are potentials? Factors of 8 over factors of that 3. And so let's list them all. Like factors of 8. I could have 1 and 8, but I could also have -1 times -8 gives me +8, right? I could have 2 and 4, or -2, -4, right? So I'm going to just put a plus minus on that. And those are factors of 8. Factors of 3 are just 1 times 3 or -1 times -3. So I'm just going to put a plus minus on that. So let's write out all our factors of 8. I have 1, I'm going to write them in order. 1 and 8, 2 and 4. I'll put the 8 at the end, right? 1 and 8, 2 and 4, right? And I'm going to put plus minus on these. Factors of 3. 1, +1, +3, or -1, -3. So I'm going to put plus minus on that. So all the potential rational zeros are, I'm going to list them all now. Plus minus, let me do them all over the 1 first. So I'm going to go 1 over 1, and then I'm going to go 2 over 1, and then 4 over 1, 8 over 1. And then I'll do them all over the 3 on the bottom. So plus minus 1 over 1, 2 over 1, 4 over 1, 8 over 1. Okay. Now I'm doing them all plus minus 1 over 3, and then 2 over 3, and then 4 over 3, and then 8 over 3. And then just double check and make sure you didn't repeat any. Like, for example, if I would have had like 8 over 4, which is 2, I would have said, oh, I already listed 2. I don't need to list it again, right? But I don't have any repeats here. So it looks like, how many rational zeros do I have? Well, 1 and -1, that's 2 of them. 2, -2. So it looks like I have 2, 4, 6, 8, 10, 12, 14, 16 of these, right? Because I have 8 listed, but there's pluses and minuses on each of these. So I have 16 possible zeros. How many zeros do I actually have? Well, this is a 3rd degree polynomial, so I have 3. There's only 3 of these that are actually zeros, right? These are just potential zeros. These are just potential zeros where it crosses the x-axis. Possible zeros. And that's all we got to do here for this one is we'll list the possible ones. We'll test it later, but let's go ahead and do this next one where we list them first. So possible rational zeros. So it's factors of that 20, factors of the 20 on the end, over factors, it looks like just a 1 there. Factors of 1 on that one. So like factors of 20 would be 1 and 20, 2 and 10, plus minus, 4 and 5. And then factors of 1, I just got 1 and 1, right? So possible zeros So we got the 1 over 1, we got 2 over 1, we got 4 over 1, 5 over 1, 10 over 1, 20 over 1. So that's our list of possible rational zeros. Now we need to find the zeros. So this is a 3rd degree. So there's 3 zeros here. So what I like to do is I'm just going to start lowest to highest. I'm going to always start with my 1 or -1, and then I test them. So what I'm trying to do is I'm taking this x cubed plus 8x squared plus 11x minus 20, and I'm going to see if, let's try -1. Let's see if -1 works. Is -1 a 0? right? Does it hit right here? Well, if negative 1 is a 0, then x minus negative 1 is a factor. And I would have to do this division and make sure that there's no remainder when I do that. So let's go ahead and test it. Let's see if negative 1 works. Let's divide it. So 1x cubed, 8x squared, 11x minus 20. And what I want is I want to have no remainder there. If there's no remainder, I know it's a factor. I know it's a 0, right? So let's run through it. 1 drops down. 1 times negative 1, 8 minus 1, 7. Negative 7, 11 minus 7, 4. 4 times negative 1, negative 4. Negative 24. Okay. No. I got to have no remainder. So this is not a clean factor. So I'm going to throw out negative 1. I've tried negative 1. It did not work in my list of possible rational zeros. So I'll say, all right, negative 1's no good. What about positive 1? Let's go to the next one on my list of possible zeros. How about positive 1? Does it hit right here at positive 1? Well, if it does, then it'll factor cleanly. So let's try it. So if 1 is a 0, then x minus 1 is a factor. Let's see if this will work. So I drop the 1 down. 1 times 1, 1. 8 plus 1, 9. 9, 11 plus 9, 20. 20 times 1, 20. Hey, there it is. Okay, I got a 0 as the remainder, so it's a clean factor. So I can put in up here, that's 1x squared, 1 degree less, plus 9x plus 20. And now that it's a quadratic, I'm really happy because I can just factor that x squared plus 9x plus 20. That'll factor into x plus 4 and x plus 5. And so I've just found my zeros here. 1, negative 4, negative 5. See, I had 3 zeros. This is a third degree polynomial. I have 3 zeros. And we've already actually factored this. So it says use the zeros to factor the polynomial. We had it factored. That's how we found them anyways. We kind of did it all at once. There's our zeros that we use to factor this thing. All right, let's look at this next one here. We've got what are the possible rational zeros? Let's list that. So that'd be factors of that 6 on the end over factors of 3 at the beginning. Well, we know factors of 6 are 1 and 6, as well as 2 and 3. Factors of 3 are just 1 and 3. So we got plus minus 1 over 1, plus minus 2 over 1, plus minus 3 over 1, plus minus 6 over 1, and then we're going to do all over the 3 on the bottom now. So plus minus 1 over the 3, plus minus the 2 over 3, plus minus the 3 over 3, plus minus the 6 over 3. Let's see if I have any repeats. Notice I have 3 over 3, but I've already listed 1, plus and minus 1. So I don't need to list that again, right? I also have 6 over 3, but I've already listed 2, plus and minus 2. So it looks like I'm left with 2, 4, 6, 8, 10, 12. 12 of these things, plus and minus, right? 6 left. 6 unique numbers left, plus and minus of each. So 12 possible zeros. Now, how many zeros do I actually have? I have 4. This is a 4th degree. Now, I don't know if they're all real zeros. We'll talk more about what if we have a complex zero, but I do have 4 zeros by the fundamental theorem of algebra. So let's go ahead and find the zeros, testing this one by one. Let's start out with our polynomial here, 3x to the 4th minus 11x cubed minus x squared plus 19x plus 6. Let's try the negative 1. Does it hit at negative 1? 3, negative 11, negative 1, 19, and 6. Hey, we got lucky. No remainder. So negative 1 is a 0. That means x minus negative 1 is a factor. It is a factor. Alright. So now I have, let's go ahead and put in 3x to the third minus 14x squared plus 13x plus 6. Okay. So now I got a factor. This is a cubic. I don't have a quadratic, so I can't just factor it straight up, right? So let's just make sure that I don't have a double 0. Let's make sure I don't have a double 0. So let's see if negative 1, like a repeated 0. Let's just test. Let's see if x minus negative 1, let's see if negative 1 is a repeated 0 or not. So now I'm going to do this division. 3x cubed minus 14x squared plus 13x plus 6 divided by negative 1. So 3, negative 14, 13, and 6. And let's just make sure this is not a repeated 0. Okay, that did not work. So negative 1 is not a repeated 0. So I'm done with negative 1. It was a 0 one time, right? And I'm going to move on to something else. So we could try like positive 1 instead. So let me erase this. So let's try positive 1. X minus 1. So let's try 1. Let's see if that'll work. Okay, positive 1 is not a 0. Positive 1 is not a 0. Let's jump to our next one on our list, which would be 2. So now I'm testing, does 2 work? So if 2 works, then x minus 2 is a factor. So I'm multiplying that. I'm sorry, dividing that divided by x minus 2. Let's see if 2 works. Hey, there it is. It does work. I have no remainder. So 2 is a 0, which means in green, x minus 2 is a factor. And now I'm going to put in 3x, 1 degree less than the red, squared, minus 8x minus 3. So let's see what we got here. I got x plus 1, I got x minus 2, and then does this thing factor? So like this will factor, I think that's 3 and 1. That's going to have to be minus plus. So there's our 0. So we got negative 1, we got 2, this will be a negative a third, and 3. There's all 4 of our zeros. Negative 1, 2, negative a third, and 3. And we've already factored that. Let's just write it out. X plus 1, x minus 2, 3x plus 1, x minus 3. This would be a good you try it problem if you want to pause the video, start listing them, and then start testing them. Now that you've tried that, let's go ahead and list out our possible rational zeros. So we got factors of that 4 on the end right there over factors of the coefficient of x to the 4 factors of 1. So we've got factors of 4 plus minus 1, 2 and 2, and 4, 1 and 4. So we got 1 over 1, 2 over 1, and 4 over 1. So let's find our zeros. So we've got this. Here's our function, x to the 4 plus 4x cubed plus 3x minus 4x minus 4. Let's go ahead and see if negative 1 works. If negative 1 works, then x minus negative 1. If negative 1 is a 0, then x minus negative 1 is a factor. So we'll go ahead and do the division. Let's test it. 1, 4, 3, negative 4, negative 4. Drop that one. Hey, it is. All right. It is a 0. So it'd be 1x to the third plus 3x squared plus 0x minus 4. Let's just make sure it's not a repeated 0. So let's see if -1 is a factor again as we divide it. Let's just double check it's not a repeated 0. Okay, that doesn't work. So it's not a repeated 0. Not a repeated 0. So we got to try, we got to move on from -1. -1 was a 0 one time, right? It worked one time. Let's go to +1. So let's go to +1. Does +1 work? So if 1 is a 0, then x minus 1 is a factor. Let's test it. 1x cubed plus 3x squared plus 0x minus 4. Does 1 work? It does. Okay. So that'll end up being x squared plus 4x plus 4. So 1 works. And we can go ahead and now we can factor that. So we got -1, 1, -2 with multiplicity of 2, meaning it just touches right there. But we don't need to write the repeated 0. And let's go ahead and write it out factored. All right, here we've got a third degree, 12x to the third. Let's list our possible zeros, possible rational zeros, factors of that 1 on the end, that -1 on the end, over factors of 12. So we got plus, minus, 1, and 1. Factors of 12 would be 1 and 12. I got 2 and 6. And I got 3 and 4. So we got plus, minus 1 over 1, plus, minus 1 over 2, plus, minus 1 over 3, plus, minus 1 over 4, plus, minus 1 over 6, and plus, minus 1 over 12. Of course, this is a third degree, so I'm going to have 3 zeros, right? It's a third degree fundamental theorem of algebra, 3 zeros. So let's go ahead and find the zeros. Now, it did tell us nicely, nice enough, they gave us one of them. Hey, good. That'll start us, right? F of 1/4 equals 0. So if I'm going to start this, I'm going to use that information instead of just starting this thing blindly. Notice I put in a 0x. Okay, so 1/4 is a 0. So x minus 1/4 must be a factor. 1/4 is a 0. 12x cubed, 13x squared, 0x minus 1. We know that'll have no remainder. 12 times a 4. 12 fourths is 3. 13 plus 3 is 16. 16 times a 4. 16 fourths is 4. 0 plus 4, 4. 4 times a 4 is 1. 4 fourths. -1 plus 1, 0. So there it is. 12x squared plus 16x plus 4. Now notice on this that I can take a 4 out of each of those. And I'd have 3x squared plus 4x plus 1. That'll make life much easier. And in fact, what I'm going to do is I'm going to distribute that. 4x minus 1. See how that still gives me a 0 of 1/4? Okay, but I don't have a fraction in there anymore. Okay, but I've got a quadratic left. So here's 4x minus 1. That gives me the 1/4 0. And 3x and x, 1 and 1. Looks like it's got to be a plus and a plus. And that will be the rest of my zeros. So I get a 4th I get negative 1/3, and it looks like negative 1 would have started us on our way. It's doing that as well. Let's go ahead and write it in factored form. 4x minus 1, 3x plus 1, and an x plus 1. All right, let's get into the intermediate value theorem to finish off this section. This is actually a simplified form of the intermediate value theorem. Let me give you a more powerful form of the intermediate value theorem. If f is continuous, let's let f be continuous on an interval from a to b. If I have some k value that's between f of a and f of b, I'll make this visual for you, then there must exist a c value in that interval such that f of c equals k. Okay, let's make this visual. So I'm going from, let's do a right here and b right here. And I've got some continuous, let's say it's like some polynomial or something. Whatever, looks like this. Okay, so it goes from this f of a, goes up to this f of b up here, f of b up here. Okay. Now this intermediate value theorem is saying if I've got some k in between there, some y value in between f of a and f of b, right? Then that means there's some corresponding c that's in between a and b, such that f of c equals k. Such that when I throw c in, it'll spit out k, right? That's all it's saying. Okay. How do we use it? Well, we're going to use it to guarantee zeros on intervals, is how we're going to use it. So this first example says, determine whether the intermediate value theorem guarantees that the function has a zero on the interval from 0 to 1. Well, let's throw in 0 and let's see what we get. If I throw 0 in, looks like I get negative 1. Okay, so when I throw in when I throw in 0, I get negative 1, that point right there. Now let me throw in the b value. It goes from a to b. My b value is 1. When I throw 1 in, I get 12 plus 30 is 25 minus 1, I get 24. So f of 1 is way up here at 24. Okay, it's kind of off. But remember, this is a polynomial, so it's got to be smooth and continuous. So I don't know what this looks like, but it's got to get up there to that 24, which means it's guaranteeing us a 0 between there. We must hit the x-axis between there. Why? Because I'm going from a negative to a positive y value. So if I'm changing signs, I've guaranteed a 0 for a polynomial function by the intermediate value theorem. So we say, does it have a yes? So by intermediate value theorem, since 0 is between f of 1 and f of 0, right? I'm going from a negative to a positive, right? This was a negative 1, that's a positive 24. Then there must be some c in between 0 and 1 such that f of c equals 0. I've guaranteed it. So that's a formal proof there if you want to guarantee the existence of by the intermediate value theorem. All right, let's look at one more here. Let's see if the intermediate value theorem will guarantee the existence. This is my a and b. Let's throw the 1 in. Let's see what we get. Looks like this f of 1 ends up being minus 5 plus 9, 8. Right? Now let's throw the 2 in. So our 2 ends up being 123. So I've got 1 up here, 8, 1, 8, and then 2 clear up here at 123, right? So there's some polynomial I have not guaranteed it because I'm staying positive. So there's no way I can guarantee the existence of a zero between there, right? So since, therefore, since f of 1 is positive and f of 2 is positive, no conclusion can be made about zeros between there on that interval. Like there might be, but there might not be. We don't know. Haven't guaranteed it at least. Well, thanks so much for taking notes. See you next time.